So the periodic table is topic 3 on the IB syllabus, and there are some very basic terms that we need to use when we refer to the periodic table, and some basic organizations that we should also know about the periodic table. So in general, the table gets ordered, the elements get ordered by increasing atomic number. We refer to columns in the periodic table as groups, or sometimes we refer to them as families, because elements that are in the same column tend to have similar chemical properties, and that is related to them having the same number of valence electrons or having the same valency. Not terms that the IB is going to use so often, but definitely you should know what a group on the periodic table is. And they're numbered in order from 1 on the left all the way over to 18 on the right. The periods are the rows of the periodic table, and for elements to be in the same period, that means they have the same number of occupied principal energy levels. And so what that means is that if I tell you the period number and the group number, you should be able to locate the element. And even if you don't locate the exact element by symbol, you would know about its electron structure. So if something is in period 3 and group 15, then that means it has 3 energy levels with electrons in them. And since it's in group 15, it has 5 valence electrons. So you can pretty easily know some information about the atom just from knowing the group and period numbers. Some other ways we're going to talk about the periodic table is by the orbital blocks that we've already looked at, the S, P, D, and F blocks. So you should be able to identify which of these blocks an element is in. Probably the only strange exception to worry about is helium, which is technically part of the S block, even though it's listed over here on the right. You should be able to determine whether or not an element is a metal or a nonmetal, or a metalloid, or a semi-metal as they're sometimes called. The metals take up about 2/3 of the periodic table, the lower left-hand side. All of the non-metallic elements are at the top right, with the exception of hydrogen, which is also a nonmetal. And right where the metals and the nonmetals meet are elements that have sort of in-between properties. And so they are referred to as metalloids, and they're on this little staircase in between the metals and the nonmetals. We'll talk more about metallic bonding and the properties of nonmetals when we look at the bonding topic. But for now, start to learn the distinction of where they're located on the table. The F block is also made up of metals. We can also look at the periodic table and learn different names for different groups. And there are certain ones that you are supposed to be aware of for the IB exam. So you don't have to know this one. I'm going to cross it out. You should know that group 1 elements are all, with the exception of hydrogen, are referred to as alkali metals. So you should know group 1 refers to alkali metals. You should know that by name. Group 18 are the noble gases. Group 17, the halogens. Groups 3 to 11 are the transition metals, not 12. Those are not transition metals. And then down here in the F block, the first row gets referred to as the lanthanoids based on the element here, La, that's right here, 57. And then these ones based on AC are the actinoids. So those two names are probably less important. It's a lot more common to talk about alkali metals, transition metals, halogens, and noble gases. Now, our modern periodic table was sort of, the foundation for it was laid down by a guy named Dmitry Mendeleev, who wasn't the first person to notice that there were some patterns that could be observed in the elements, but he sort of formalized it and put a lot of the current rows and columns into place in his original version of the periodic table in 1869. It's important to note that when he created this table, the electron had not been discovered and wouldn't be discovered for almost 30 more years. And since now we mainly associate the periodic table as being based on electron configuration and the number of protons, it was really a pretty incredible table that he came up with, an incredible organization considering no one knew anything about protons or electrons at this time. The key concept really to take away from what Mendeleev did is this concept of periodicity and calling the table periodic, because it could just be called the table of elements, but it's called the periodic table of elements. And it's called that because the elements show repeating properties at regular intervals. So the reason why we've put all these alkali metals into the same group is because lithium, sodium, potassium, rubidium, etc. have very similar properties. And neon, argon, krypton, and helium have very similar properties. That's why helium was placed in this group. So the periodic table is far more useful than just a random list or table of elements. Because of its unique organization, we can see and know about these repeating properties, and the term for that is periodicity. Now, there are a number of other periodic properties that we're going to look at. First, ionization energy is a big one. Electron affinity is not as important of a periodic property, really, but we should know how to define it and how to represent it in a chemical equation. We're also going to look a lot at atomic radius, which is essentially the size of an atom, ionic radius, which is the size of ions, and a property called electronegativity, which is when you're looking at when atoms are bonding, how strongly do they attract the electron pairs to themselves when they're bonding with one another. So it's a relative measure that has to do with how well atoms attract electron pairs. So notice that these top two properties get measured on individual atoms, whereas these other properties down here are measured actually when things are bonding. So we're going to see subtle differences between the two. But really, they can all be explained if we can wrap our head around a concept known as effective nuclear charge. Sometimes it'll be referred to as effective Z or Z effective. And the effective nuclear charge is basically the net attraction that electrons experience from the nucleus. So the nucleus is positive, the electrons are negative, we know that, and the valence electrons are the outermost electrons, so they're usually the electrons we're concerned with. And so based on the details of an atom structure, we should be able to predict with a decent amount of accuracy how two different atoms compare for how strongly their electrons are attracted to the nucleus. So essentially, if I said something had a higher effective nuclear charge, that would imply that that atom's electrons are more attracted to the nucleus than another atom. So what affects effective nuclear charge? Well, the most important thing, if you're comparing two atoms and you want to know which will have a higher effective nuclear charge, a greater attraction for its electrons, the first thing that you should look for is the number of occupied principal energy levels. So not full principal energy levels, but just how many electron energy levels does it have? And the higher the principal energy level for an electron, the farther it is from the nucleus. And that means that the Z effective, the nuclear attraction, will go down. So when electrons are farther from the nucleus, they experience less attraction to the nucleus. But actually, that effect is so big that when you're in the second energy level, you experience a far less attraction than in the first energy level, really even more so than you might predict just from the difference in distance from the nucleus. And so that brings up a very important concept called the shielding effect, that when there are inner shell electrons, so electrons in between a nucleus and a valence electron, those inner shell electrons end up blocking the positive charge of the nucleus to some degree because they repel the valence electrons. So inner shell electrons actually repel valence electrons outwards and end up sort of minimizing the attraction felt by valence electrons for the positive charge of the nucleus. So even though as you get more protons in the nucleus, you might expect it always to pull in electrons more strongly. When electrons are in farther away energy levels, well, one, they're farther away, but two, there are all these extra inner shell electrons that are shielding them from the positive charge of the nucleus. So being in a higher energy level puts the electron farther from the nucleus. That's one really important idea. It also increases the shielding effect felt by the outer electrons. And so the combination of being farther away and having a greater shielding effect, both of those factors mean that the higher energy level an electron is in, the less attracted it is to the nucleus. If you're comparing two atoms that have the same number of principal energy levels, so two atoms that are in the same row of the periodic table, they're going to have the same number of principal energy levels. So you can't use either of these arguments to explain which one might have a higher effective nuclear attraction or a higher effective nuclear charge. So what do you do? Well, first, it's usually important to point out that they have the same number of principal energy levels. Because that's such a big deal, it's such a major impact on this concept of Z effective, it's a good idea to point out that they have the same number of principal energy levels first. Once you've done that, the next thing to focus on is the number of protons. And since protons are positively charged, if you have more protons in a nucleus, it should create a higher effective nuclear charge for electrons. So what we'll see as we go from left to right across any row of the periodic table, the general trend is that electrons get more attracted into the nucleus because the shielding effect is remaining the same, but the number of positive charges is going up, and therefore the outer electrons are getting more and more attracted. And finally, the last thing to concern yourself with, and this only comes up in very particular rare circumstances, is you can sometimes be asked to compare particles that have the same number of principal energy levels and the same number of protons. This could really only happen if you're dealing with an atom compared to a negative ion. So what I mean by that would be like if we compare the fluorine atom to the fluorine ion, which is F1 minus. So these two particles, the fluorine atom and the fluoride ion, both have 2 energy levels with electrons in them, and they both have 9 protons. So we can't use either of the arguments from above to compare which one should have a stronger attraction for electrons. So the thing we must talk about now is the number of electrons that they have. Since they have the same protons and the same shielding effect, the one that has more electrons will experience less attraction for the nucleus because the extra electrons create more electron-electron repulsion. So we would expect the electrons in the fluoride ion to be less attracted to the nucleus than the ones in the fluorine atom. So those are the ideas that explain effective nuclear charge. Effective nuclear charge is not a term you get asked to define on the IB exam, but it's one that you can use to explain how different elements will compare for their periodic properties, things like ionization energy and atomic radius. So again, you walk through, look for comparing the number of occupied energy levels, followed by the number of protons, followed by the number of electrons.